Hi folks, Ms. Stryker here, getting ready to record my first video of the year for AP Physics C. I like to start the year with a quick review of electrostatics. And usually it is a review, but this year it's not a review for some of us because last year was cut short. We all had to go home at the beginning of March, and I know that I was just getting ready to start electrostatics in AP1, and I think Mr. Keller was doing the same thing. And so we didn't ever get to electrostatics last year. I think if you took AP1 and 2 last year, you did some electrostatics, so we might be in different places. But I would like to bring those students who didn't ever learn Coulomb's law up to speed in this quick intro video. All right, so that is my intention. I'm actually going to draw on my tablet here. And so I'm going to flip down my tablet. Right now you're looking at me. I'm in my kitchen in Northampton. But when I flip this down, you're going to see my ceiling. And that won't be very interesting. So I'm just going to close my little window so that you don't see me anymore once I flip this down. And then I'm going to give you a quick intro into Coulomb's law and charge. All right, and so here we go. I am flipping. And then let's see if I can get rid of this. There we go. I think it's gone. Hopefully it is for you too. It's gone for me anyway. So, so what is Coulomb's law? Let me just start there. So Coulomb's law really is a force rule. It's a rule that describes forces. And the forces that it describes are between electrostatic charges. Charged objects, objects that have a charge. Okay, so what is a charge? Well, a charge, you probably know, can be positive or negative. And what's the positive charge? Well, it's a proton or many protons. What's the negative charge? It's an electron or many electrons. So positive charges we tend to denote with a little plus. Negative charges we tend to denote with a little minus. Of course, there are neutral charges as well. Those are called neutrons. You already know from chemistry, there are protons and neutrons inside the nucleus, and the electrons sort of swarm around the outside of the nucleus. In physics, we denote charge using the letter Q or positive Q. Could be lowercase or uppercase. I didn't mean to say positive. Lowercase or uppercase Q denotes charge. Okay, and the unit is a Coulomb. So I tend to write units in these little square brackets. Okay, a Coulomb is a ton of charge. It's a lot of charge. So we use prefixes to reduce that Coulomb down to smaller quantities. And so you'll commonly see microcoulombs. So that's 1 times 10 to the negative 6 coulombs of charge. You might see nanocoulombs, which is 1 times 10 to the negative 9 coulombs of charge. So we tend to use metric prefixes to reduce the amount of charge because a Coulomb is just a ton of charge. All right, elementary charges. So 1 electron has a charge of 1.6 times 10 to the negative 19 coulombs. And you might be going, wait a minute, it's negative. Yes, it's negative. I could put the negative there if I want. It doesn't really matter. Okay, there's the charge of an electron, and of course the charge of a proton is positive 1.6 times 10 to the negative 19 coulombs. Yes, you can put a plus there. It doesn't really matter. 1 proton. You can't reduce charge to half of an electron or half of a proton. This is called the elementary unit of charge. You can't have half of that or a third of that or a fourth of that much charge. Charge comes in discrete quantities that are multiples of this amount. Okay, you can't have half of an electron or half of a proton. And so sometimes we use the symbol E to mean fundamental charge. Okay, and it could be positive if it's a proton, it could be negative if it's an electron. All right, and so that's what charge is. The symbol is Q, small q or large q. It's measured in coulombs. A coulomb is a huge amount of charge. Another way to think about that is that if I'm interested in an electron, so charge for one electron is 1.6 times 10 to the negative 19 coulombs per electron. So you might say, well, how many electrons makes up a coulomb? 1 coulomb charge. And then I could multiply that by, well, now I need a conversion factor. There are 1.6 times 10 to the negative 19 coulombs in 1 electron. And so this, if I multiply 1 by 1, and I divide by 1.6 times 10 to the negative 19, coulombs cancel, and I get the charge in electrons of 1 coulomb, right? So 1 coulomb is equal to, and I just took that 1 coulomb and converted it into how many electrons. And so go ahead and do that on your calculator. 1 divided by 1.6 times 10 to the negative 19. It's a huge number. A huge number of electrons make up 1 coulomb of charge. 6.25 times 10 to the some big number. All right. And so a coulomb is a lot of charge. So that's the background. So now let's go back to Coulomb's law. You know that you can charge objects up by, for instance, you can charge a balloon up by rubbing it on your head or by rubbing it with any amount of animal fur. All right, so there's my balloon. If I rub it on my head, what happens? My hair gives up some of the electrons that are normally in my hair, and this balloon picks up a negative charge. If I take a second balloon and I rub it against my hair, it also picks up a bunch of negative charge. And now these balloons will repel. So you probably learned these rules back in middle school, maybe even elementary school. Like charges repel, unlike charges attract. And another interesting rule is that any charge will attract a neutral object. Well, these words attract or repel, really denote forces that exist. And so, since you took physics last year, if these two balloons are repelling, that means they're going to be pushing away from each other with some force. And those are equal and opposite forces. So if I call this balloon 1 and this balloon 2, this force, the force that acts on balloon 1 due to balloon 2, and here's the force acting on balloon 2 due to balloon 1, those are equal and opposite forces, and we can actually find the size of that force if I know the charge and if I know the distance between those balloons. So let's just make up some charges. Let's say that the charge on balloon 1 is equal to, let's just say 10 extra electrons. I have 10 extra electrons, so 1.6 times 10 to the negative 18 coulombs of charge is 10 electrons. And the charge on balloon 2 is, I'm just going to make something up, 3.5 times 10 to the negative 19 coulombs of charge. All right, so some smaller value of charge. Actually, I want this to be negative 18. Negative 18 coulombs for no good reason, just to have some similarity between those exponents. And what about the distance? Let's just say it's 1 centimeter. And we're going to use significant digits. So I'll say 1.0, 1.0 centimeters. That gives me 2 significant digits. So there's the stuff that I need to write down this force law. And so Coulomb's law says this: the force that exists between two charges is equal to some physical constant, K, and K happens to be equal to 9 times 10 to the 9 Newton meters squared per Coulomb squared. Similar to the gravitational constant in that it just exists as a multiplier when you're using Coulomb's law, times the charge on one object, times the charge on the other object, divided by the radius squared, or the distance between those objects squared. And commonly, these are put in absolute value. That's why I keep saying it doesn't matter whether it's a positive or negative charge. It really doesn't matter. What matters is what you see when you draw the picture. I see these are repelling. I'm making them push away from each other, right? If they were on top of each other, if one balloon was on top of the other, the forces would be going up and down. So you need to know what repelling means. It doesn't necessarily have to be associated with a positive force or a negative force. So in this case, plugging in, the force between those objects is going to be 9 times 10 to the 9 Newton meters squared per Coulomb squared. Charge on the first balloon, 1.6 times 10 to the negative 18 coulombs. Second balloon is 3.5 times 10 to the negative 18 coulombs. And I'm going to divide that by the distance in meters squared. Okay, 1 centimeter, 0.01 meters squared. And notice, and this is a meter, so I don't want to be too sloppy. Meters cancels with meters. Square coulombs, and I have a coulomb and a coulomb. I'm going to be left with newtons. So my charges need to be in coulombs, and my distance needs to be in meters, and I'll get my force in newtons. So I'm going to pause this video, look for my calculator because I don't have any idea where it is, and come back, and you can do this calculation while you're waiting for me, hopefully. All right. All right, here we go. So I did my little calculation. I did find my calculator, and just wanted to show you a sort of a cheater method. If you don't have your calculator, or you only have a very simple calculator that does maybe add, subtract, multiply, and divide, you can do 9. Let me not use that. You can use 9 times 1.6 times 3.5. And if you do that, you get 50.4. So multiply these are called mantissa, the first thing you write down when you're using scientific notation. If you multiply those values, that gives you the first part of your solution. And then you just need to keep track of your exponents using exponent rules. So 9 minus 18 minus another 18. And then negative 2 squared is going to be negative 4 in the bottom. And so what I did was do 9 minus 18 plus 4, because I know I'm dividing by that negative. And that's where I got the negative 23. Okay, so then I took my calculator out, and sure enough, my calculator gave me 5.04 times 10 to the negative 22 newtons. And that is the force between those very lightly charged balloons. Okay. So that's how to use Coulomb's law. Another example of using Coulomb's law is to take some charges that are not arranged in a nice line, but might be arranged in an equilateral triangle, and try to find the force acting on any one of those charges. And so let's say this is an equilateral triangle where the distance between each charge is, let's just say 0.12 meters. And that's the same distance here and here. So 0.12 meters. And let's give these charges numbers. This is charge 1 is up top, and charge 2 and charge 3 is right here. 1, 2, and 3. And then I'm going to write down some sizes. So let's say Q1, it's a negative charge. And so I'm going to make it about 2.5 microcoulombs. And Q2, and by the way, it's a negative 2.5 microcoulombs. It's a negative charge. Q2 is positive. I made that one positive. So let's call that 3.7 microcoulombs. And Q3, which is also positive, how about 4.1 microcoulombs? And let's say I want to find the total force. On, it doesn't matter which charge you pick. So I'm going to say find the total charge on charge 2. Total force on charge 2. Well, we know that forces add. Okay, so I'm going to use maybe red to show the two vectors. And so I know between charge 1 and charge 2, since they're opposite charges, there's going to be some attraction, right? In fact, those, there are actually two forces involved there. The force of charge 1 on charge 2 and the force of charge 2 on charge 1. But I'm only interested in the total force acting on charge 2. So I'm only going to draw that force, all right? And it's attractive. And I'm just going to name it the force between 1 and 2. Now I've got another force here, the force between 2 and 3. And I see two positive charges, so that's going to be repulsive. All right, and I'm going to draw that force to look like this. Now I know that there's another force that looks exactly the same on charge 3, but I'm not so interested in it. Okay, so this is the force between charge 2 and 3. That's what those forces look like. I could even imagine what the angle between F12 and the x-axis is going to be. It's going to be 60 degrees. And I know that F23 is acting exactly along the x-axis in the negative direction. So the next step in finding the total force on charge 2 would be to figure out what those individual forces are. And so I'm going to work in order. So F12 is going to be 9 times 10 to the 9. That's the K value, Newton meters squared per Coulomb squared, times the two charges. What is charge 1 and charge 2? So 2.5 microcoulombs. And then 3.7 microcoulombs. You may need to look up what micro means or nano means if you're given some prefix that you're not sure of. And then I'm going to divide that by the distance between them, 0.12 meters squared. And I'm going to get that answer. I'm going to do that very quickly on my calculator right now. So 9 times 10 to the 9 times 2.5 times 10 to the negative 6 times 3.7 times 10 to the negative 6. Divide by 0.12 and square that value. I get 5.78. 5.78 newtons. I'm going to leave that with 3 digits. I'm eventually going to round to 2 digits, but right now I'm leaving it at 3. And now I need the force between 2 and 3. All right, so again, the same K value, 9 times 10 to the 9. I'm going to be sloppy and not write down my units. So force 2, or charge 2 rather, is 3.7 times 10 to the negative 6 coulombs. And 3 is 4.1. Charge 3, 4.1 times 10 to the negative 6 coulombs. And divide again by the distance between those two charges, 0.12 meters squared. And so let's just do that calculation. I wonder if you can hear me typing out on my calculator. So I get 9.48 newtons. And again, I'm leaving that as 3 significant digits. So you can see that these vectors, and these are vectors, have a size. I've written the size down, but they also have a direction. And so in order to find the total force, I really need to add those vectors tip to tail. And remember what happens when you add tip to tail. I'm going to come down here and do that. If I take a vector 1, 2, which points at 60 degrees, and I add it to vector 2, 3, which is a little bit bigger, and I add the tip with the tail. Notice right there where they're adding together, there's a tip combined with a tail. I get my sum vector from the start to the finish that's going to point like that. So I need this size and I need that direction in order to give the total vector. So what I'm going to do is write each of these vectors in component form. So F12 is going to be so much in the x direction and so much in the y direction. I'm going to call the x direction I and the y direction j. And then I'm going to do the same with F23. It's going to be so much in the x direction and so much in the y direction. Okay, so I'm going to take my 5.78, multiply it by the cosine of 60 degrees, and that's going to give me, and I should really check my mode on my calculator to make sure I'm in degree mode. It gives me 2.89 for the x component, 2.89 in the x direction, and then 5.78 times the sine of 60, and that should be, looks like 5.01 in the y direction. And then I just check to make sure that that seems to make sense. A little bit in the x direction, a lot in the y direction. Yeah, that makes sense. What about force 2,3? Force of charge 2, or the force between charges 2 and 3. Well, that points straight back. So it's negative 9.48 in the x direction and nothing in the y direction. So in order to get the total force, I have to add these together. The total force, or the resultant force, so 2.89 minus 9.48, negative 6.59. In the x direction, that little I hat means in the x direction, and I'm calling it I hat. That unit vector is kind of like having a hat on it. And then what do I have in the y direction? I have 5.01 in the y direction, and y direction means j hat. All right, so my total vector goes back 6.59 in the x direction and up, not quite as much, 5.01 in the y direction, and I want this total vector. So now I use the Pythagorean theorem. Square root 6.59 squared plus 5.01 squared, 8.27. Now I'm going to write it as 8.3 newtons. And last but not least, I need the angle at, using inverse tangent, looks like 37 degrees. And I might say, north of west? Or you could write that the total force is 8.3 newtons at an angle of 180 minus 37 is 143 degrees. So if you don't specify north of west, if you don't specify a direction, the default is that you're measuring from the positive x-axis. And so there's 143 degrees there. All right, so that is my total force acting on charge 2 due to 2 other charges. This is a great review of how to add vectors together using components. And so hopefully it wasn't too painful for you to watch.